Well, welcome back from your extended break. Honestly, it's been so long since we've met that I've almost forgotten where we left off before the break. So if I've almost forgotten, then probably you have too. I know that we had a test right before the break, but then before that test, I believe we started covering this idea of using undetermined coefficients to solve these differential equations. But since it's been so long, I'm going to go ahead and just kind of run through this method real quick with you, and then once we go through this video, you'll be ready to do the 4.4 homework. One thing I'll mention about homework, if you've read the updates I've posted, then you know that homework's going to be on my lab as long as we're doing class online instead of doing our presentations on Tuesday, because obviously we can't do that anymore. So the way this will work is I'll record these videos. What the screen that you're seeing right now is essentially like a whiteboard. I'll be able to write on it as I talk. And when I can, I'll maybe find YouTube videos or videos from Pearson to use as well. But at least for this chapter, the videos I was finding online, they weren't really helpful, or I didn't think that they would be helpful. So I wanted to kind of talk through things kind of the same way we would normally talk through them in our regular class. So regardless of how much of 4.4 we covered before the break, let's just pretend like we're starting fresh with this topic. So the last thing you had to do on your exam was solve homogeneous linear equations, second order linear equations. Homogeneous meaning that the right-hand side of the equation was a zero. Okay, so we know how to solve those, but now in chapter 4, or in section 4, we're starting to learn how to handle it when that right-hand side is not zero. That's what makes it a non-homogeneous equation. And really, when I was looking on YouTube for some example videos, most of them I couldn't even pick because they couldn't even say non-homogeneous correctly. They were saying non-homogeneous, which is a completely different word. So anyway, with that aside, let's talk about how to solve these things. Remember, the idea is that we're this second order linear equation is basically modeling a mass on a spring, and this function on the right hand side is giving us some sort of forcing function or some kind of external force acting on that mass on the spring. Okay. To solve these non-homogeneous equations, one basic approach is to just basically, I guess what the solution is going to be. Okay, so this is what we call the method of undetermined coefficients. We can find some specific solution to the equation just by looking at this function f of t, and based on what that function is, we can make an educated guess about what the solution might be. So that's what we'll be doing in this lesson. So when we're solving a y double prime plus by prime plus cy equals some function f of t, and we're trying to figure out what function y works in this equation, the idea is that we can let this function f of t help us make an educated guess of what a solution might look like. One thing I need to mention here, when we're finding these solutions, we're finding what's called a particular solution. That's why we write this y sub p. We're not finding the general solution yet. We'll talk about that in the next section. All we're doing here is finding one specific solution that works in this equation, and then we'll figure out how to get the general solution with those arbitrary coefficients later. So now the idea is that if I look at this function f of t on the right-hand side of this equation, and that function is some kind of exponential function, then it makes sense that my solution will also be some kind of exponential function. So I make this guess that the solution is some number times e to the kt, and then my goal is to plug this function a e to the kt into the differential equation and see if there's some number a that makes it work. If it works, great. If it doesn't work, then there's other things we can do to try to figure out a solution. Same thing for the other two scenarios. If that function on the right-hand side involves sines or cosines, then it makes sense that our solution will also involve sines and cosines. So for example, if I have a sine of 3t on the right-hand side, well, let's think about what's going on with this differential equation. I'm doing two derivatives of some function plus the derivative of some function plus the function itself, and after doing all of that I end up with something involving the sine function. It makes sense that the thing that will work in this equation will be something involving either sines or cosines, because when I take the sine derivative of sine I get cosine, when I take the derivative of cosine I get negative sine, so something involving sines or cosines should work. So we make our guess, and our guess will be that we have a combination of sines and cosines. We have some number times the sine function plus some number times the cosine function. Those two numbers, a and b, are our undetermined coefficients. We'll plug this guess into the equation and see if there are specific numbers a and b that make this guess work out for us. And again, if they don't work out, then we'll have some other approach we can take. The third case, same idea. If the right-hand side is just an nth degree polynomial, then it makes sense that the solution is probably also going to be an nth degree polynomial. So we make a guess. For example, if it was a second degree polynomial on the right-hand side, then maybe I would guess that my particular solution is also a second degree polynomial. So maybe something like at squared plus bt plus c. I would guess that maybe my solution looks something like that. I would plug that function into my differential equation and see if there were specific numbers a, b, and c that make this thing work out. If not, then I'll take some other approach. But if it does work out, great. I've got a particular solution or a specific solution to my equation. Let me show you one example that matches that third case we saw on the previous slide. Here we have y double prime plus 3y prime plus 2y equals 3t. Notice that right-hand side, the non-homogeneous piece to the equation, is a first-degree polynomial. So we're going to guess that the solution to this equation is also a first-degree polynomial. So all we need to do is plug this guess into our equation and see if there are any particular numbers a and b that make this work for us. It's not that hard to figure out that if I'm going to plug this into the equation, well, I need y double prime and I need y prime. So let's figure those out real quick. Y p prime will be a, y p double prime is 0. So plugging those into the differential equation, I have y double prime, which is 0, plus 3 times y prime, that's 3 times a, plus 2 times y, that's 2 times our guess at a solution, so that's 2 times at plus b. And all this in the end is supposed to come out to be the same thing as 3t. After some simplifying, we have 3a plus 2at plus 2b equals 3t. And when I get to this point, let me gather my constants together. So I've got 2at plus 3a plus 2b equals 3t. This is kind of a simplified version of some things you could run into, but the basic idea is that when you have a polynomial on the left-hand side being matched up to a polynomial on the right-hand side, those polynomials can only be equal if the coefficients match each other. Okay, so in this case, my coefficient on the t is a 2a, and on the right-hand side, the coefficient to t is 3. So the only way that these could be matched is if 2a is the same thing as 3. Similarly, when I look at my constant terms, I have 3a plus 2b is a constant. There's no t's involved. If I look on the right-hand side, there aren't any constants written, but you can imagine there being a plus 0 there. So the only way that these two polynomials can match each other is if 3a plus 2b is 0. So we find out that a must be 3/2. And if a is 3/2, then I can come over here and pretty easily find out what b has to be as well. That's 3 times 3/2 plus 2b equals 0. That's 9/2 plus 2b equals 0. And just a little bit more algebra, subtract 9/2 from both sides and divide both sides by 2. We get b equals -9/4. So in the end, we have a number for a and we have a number for b that makes our guess at a solution work out. So we know that this function 3/2 t minus 9/4 is a solution to this differential equation. That's just one particular solution. Again, that's why we have this little subscript p. This is one specific or particular solution to that differential equation. Keep in mind, our goal next will be to find the general solution to the equation. And to do that, we'll get something called the superposition principle that tells us how we can attach to this particular solution another function that gives us a general solution. All you're doing in your homework for this section, though, is finding specific or particular solutions to these equations using undetermined coefficients. For these next two examples, I went ahead and wrote down what our guess would be. So we have y double prime plus 3y prime plus 2y equals 10 e to the 3t. Since that right-hand side is an exponential function, we would guess that our solution is also an exponential function. Notice here we have the same number attached to t in the exponent. Okay, so that shouldn't change. The only thing that might change is instead of a 10, we have some unknown number attached to e to the 3t. That is our undetermined coefficient in this case. So, just like before, you find the derivative and the second derivative, and then plug everything into this differential equation and figure out if there's some number a that makes this work. On the second one here, y double prime plus 3y prime plus 2y equals sine of t, since we have a trig function, we are going to make a guess that our solution is also a combination of trig functions, a combination of sines and cosines. Let me mention here, if you had some number attached to t, so say this was sine of 3t, then your guess should reflect that. So my guess in this case wouldn't be sine of t, it would be sine of 3t and cosine of 3t. Alright, so if there's any number attached to the t, you guess that that number will show up in your solutions as well. But in this case, there's no number there. So we just have a plain old sine of t on the right hand side, and so we're probably going to have something involving sine of t and cosine of t for our solutions. So this is our guess, and again, we just write down yp prime, yp double prime, and put everything into this differential equation and see if you can find numbers a and b that make this all work out. What I want you to do here is pause the video and see if you can find these numbers on your own, and then after you've done that, you can check back here to see if your answer was correct. Okay, so I'm not going to go through all the work on these. These are actually taken straight from the book. This is example 2 and 3 on page 175 in the textbook. Keep in mind that if you didn't take your textbook home with you over the break and you're stuck at home without your book, since we have access to MyLab now, you also have access to the ebook through MyLab. Okay? If you need help figuring out how to open up the book, let me know, I can help you out. But if you'll just take a look at those examples, then you can see if your answer or if your work was correct. I'll go ahead and tell you what the solutions here should be. After doing all the work, you would get a equals 1/2. Alright, so then your particular solution in this case would be 1/2 e to the 3t. In this other one, you would find, after plugging everything in and solving, you would find that a is, let me find it on the page, a is 1/10, and b is -3/10. So then our particular solution in this case is 1/10. Sine of t minus 3/10 cosine t. Sorry, I'm pausing here to just make sure I use a and b the same way they used it in the book, with a attached to sine and b attached to cosine. And yes, that's the way they did it in the book. Alright, so if you did these on your own and got these answers, then it looks like you're on the right track. If you didn't get these answers, then you'll want to look at page 175 in the textbook to see where you went wrong. One last thing I want to show you guys is this example where we have, similar to the first three scenarios where the right-hand side is exponential or trig or polynomial function. That tells you what a smart guess would be for a particular solution. What we have here, the right-hand side is an exponential function, but there's also t raised to the nth power attached to it. If we see that happening, and here c, this c is just some constant, but when we see something like this, I guess for a particular solution that would make sense would be to have some kind of nth degree polynomial times e to the kt. So for example, y double prime plus 4y equals 5t squared e to the t. I have a t squared showing up, and so part of my guess is going to involve a second degree polynomial. That's what I have here, a squared, at squared plus bt plus c. And then I have an e to the t showing up, and I also have an e to the t showing up in my guess. Now again, keep in mind that if you have some number attached to the exponential function, like e to the 3t, then your guess would involve that number, e to the 3t. But in this case, we don't have a coefficient on the t, it's just a coefficient of 1, so we don't need to worry about that here. Once you make your guess, the process is really the same as what we've seen in the other examples. You take the derivative and the second derivative, plug these into the differential equation, and see what works. Here's another chance for you to pause the video and see if you can do this on your own. And then, after you try it on your own, come back and see if your answer matches. Okay, so to check your work, I went ahead and wrote down the derivative and second derivative of our guess at a solution. So the first thing you need to do is maybe pause the video here and make sure your yp prime and yp double prime match what I have written down. I may have organized my answer in a slightly different way from yours, but take a look at your derivative and second derivative and make sure that in the end they're the same thing. If they're not, then what you probably forgot is to use the product rule. Okay, this is a product of two functions, and so the derivative involves the product rule. If you do the product rule correctly, then you'll get these derivatives I have written here. Now, the next line, this whole big mess, is really just a matter of plugging things into the differential equation where they belong. So according to my differential equation, I should be doing y double prime, so I take this yp double prime, that's what this whole big chunk here is. That is my yp double prime. Again, if you take a look back at what I have written up here, you'll see that everything matches. Maybe I went ahead and distributed the 2 into the parentheses and distributed the e to the t into the parentheses. But aside from some basic distributions, what I have written here on this line matches what I have written on the line before. This whole chunk here is my 4 times y, which in this case is 4 times this function y sub p. This is 4 times y sub p. Oh, and now that I look at that, I forgot to distribute the 4 to these other two pieces. Okay, glad I caught that. Okay, so now that I've written this down, it looks like a big ugly mess, but in the end, this whole ugly thing on the left-hand side needs to match what we have on the right-hand side of the differential equation, the 5t squared e to the t. We'll do something similar to what we did before, where we compare coefficients, and to do that, I'll want to group everything together according to powers of t. So let's group together all the t squared e to the t's first. So scanning through this long line, t squared e to the t, where do I see that showing up the first time? I see it right here. And where else? I see it right here. Okay, so if I take those two terms and factor a t squared e to the t out of them, what I'm left with is an a plus 4a, which we can just simplify to say 5a. Next, I want to go through here and take care of everything that has t e to the t attached to it. So t e to the t, scanning through this line, the first place I see that is here. So that has a 4a attached to it. Okay, so that one's taken care of. Let's see, where else do I see it? I see it here. That has a b attached to it. And anywhere else? Let's see, I see another one here. That has a 4b attached to it. Okay, and then I believe that catches all of them. Alright, so t e to the t times 4a plus b plus 4b, and again, this b plus 4b, we'll simplify it, we'll rewrite it as 5b. But continuing on, next I'll look for anything that has an e to the t without a factor of t attached to it. And looking through, I see the very first term has an e to the t, so that had a 2a attached to it. And this term here, that has a 2b attached to it. And where else? Here I have a c attached to it. And any others down at the end. That has a 4c attached to the e to the t. Okay. So now if I compare the two sides to my equation, notice the right hand side I have a t squared e to the t showing up. So the only thing on the left hand side that should really give me a coefficient would be this t squared e to the t on the left hand side. So that tells me that the coefficient here, a plus 4a, should equal the coefficient on the left-hand side, which is 5. So that tells me that 5a should equal 5. All the rest of these don't show up on the right-hand side. The t e to the t, there aren't any t e to the t's on the right-hand side. So this whole coefficient here should be 0. 4a plus 5b has to come out to be 0. Similarly, the e to the t doesn't show up on the right hand side. There aren't any terms that have just a plain old e to the t attached to them. And so this whole coefficient, 2a plus 2b plus 5c, should also be 0. Alright, so this is kind of a more advanced version of comparing coefficients compared to what we saw earlier in the video. But once we get here, it's pretty easy to figure out what a, b, and c are. Right off the bat, we find out that a is 1. If I know that a is 1, then I know that 4 plus 5b should be 0, so 5b should be negative 4, and b is negative 4/5. Okay. If I plug in a is 1 and b is negative 4/5 to this last equation, I have 2 minus 8/5 plus 5c equals 0. And after some simple algebra, we get c equals negative 2 over 25. So a, b, and c were our undetermined coefficients in this guess. We made a guess at what the solution would look like, and then we plugged that guess into the differential equation and found out what those undetermined coefficients should be in order to make that guess work. So in the end, now that we know that what a, b, and c have to be in order for this to work, we have a specific solution to our differential equation. We have at squared, that's just 1 times t squared, so that's t squared, plus bt, so that'd be minus 4/5 t. Sorry, my writing's getting a little bit sloppy here at the end. Plus c, well, c is negative 2/25, so I'll say minus 2/25. Times e to the t. Alright, so again, I took this guess at my solution up here at the top. I found out what A, B, and C had to be for this to work out. And then, now once I found out A, B, and C, I could write down my specific solution to this differential equation. Again, keep in mind, this is just one specific solution to the differential equation. We know that a second order differential equation should have some arbitrary constants showing up as well. It should have two arbitrary constants showing up in the general solution. We don't have a general solution yet. All we have is just one particular solution. In the next section, we'll learn how to find the general solution.